Welcome to Affordable Tutor, and today we are mastering basic experimental designs, focusing on the completely randomized design, or CRD. Before diving into CRD, let's review the anatomy of an experiment. Key components include the experimental unit, the smallest part assigned a single treatment, the treatment itself, the sampling unit, and the measured yield. Our framework of analysis involves the design, which is the plan to test treatments, the statistical model used to present data, blocking to group similar units, and experimental error, which is the natural variation between identically treated units. Experimental design relies on three pillars: replication to estimate error, randomization for unbiased estimates, and local control to increase precision by grouping units under similar conditions. We are focusing on the three basic experimental designs. Our main focus is the completely randomized design, the foundational design for homogeneous conditions. The core rule of CRD is that it is preferred only when experimental units are completely homogeneous, meaning no existing source of variation. This is ideal for small-scale, highly controlled environments like lab or greenhouse experiments. The randomization layout for a CRD involves three steps: numbering the units, generating random numbers and ranking them, and finally, assigning treatments based on those ranks to create a randomized map. The statistical model for CRD is y_ij equals mu plus tau_j plus epsilon_ij. This model helps us estimate treatment means, standard errors, variance components, and test for significance. In CRD, the null hypothesis states that all treatment effects are equal. The alternative hypothesis is that at least one treatment effect is different. We use formulas like correction factor and sum of squares to analyze the data. The ANOVA blueprint for CRD organizes the analysis of variance. We compare the F ratio to a critical value. If the p-value is less than or equal to the significance level, the F test is considered significant. Let's apply CRD to a case study comparing the average yield of 5 different wheat varieties at a 5% significance level. We have 20 plots, 5 treatments, and 4 replications. Analyzing the results, we find calculated values for the sum of squares. The ANOVA table shows a significant F ratio and a p-value of 0.000, indicating significant differences among the 5 varieties. Visualizing the significance, variety V4 produced the highest average grain yield, while V1 and V3 were inferior in yield but not significantly different from each other. Executing CRD in statistical software like Statistix requires formatting data in simple columns. The execution path involves selecting the CRD analysis of variance and mapping the yield to the dependent list and treatment to the treatment variable. The CRD offers high flexibility and simplicity, but requires strict homogeneity. If underlying variation exists, a randomized complete block design should be used instead. If you have any question, please let us know in the comment section. Don't forget to subscribe to our channels and bell icon for latest video.